All right, so welcome back here. Let's continue the review. Section 4.3 deals with representing chemical reactions. And so the main idea here in this section, and it's not going to be a very long section, so the main thing that you need to be able to do here is to be able to represent a chemical reaction by representing each of the individual component atoms in a molecule by some kind of particulate diagram. So for example, if we take into account a very simple reaction, carbon monoxide added to oxygen, if we show this to be forming a molecule carbon dioxide, and let's say that all of these are gases, we would have to balance this out. And so here we would look at carbon, carbon, so that's fine. But here we've got 2, 3 carbons, and so we would need to make sure we have 2 copies here. So let's go ahead and do that. We'll put this as a 2. And now we've got to deal with the carbons here, 2 carbons. We've got 1 over here, so we'll need to deal with a 2 here on the right-hand side. So we've got 2 carbons on the right, 2 carbons on the left, 2 oxygens for this compound, and then 2 oxygens here. And so we've got 2 times 2 is 4, so that would put the whole balance reaction at a 2, 1, 2. Now, graphically, what you'll need to do is to be able to convert these particles over to a new way of representation. So here we're using actual element symbols, but what if we were using a couple of atoms here? Let's say that we use a key, and this is something that you'll develop, or the question will pose this for you. Let's say that we're looking at carbons to be represented as blue dots, and let's say that we have red dots here for the oxygens. So what you would want to do here is go ahead and represent it. So at a basic level, we would represent essentially a carbon monoxide molecule. We would represent that as 1 carbon, which would be blue. We would represent that with 1 oxygen, so that would be a carbon monoxide molecule. And then since we have 2 copies, at least the way the mole ratio here shows it, or the coefficient says that we've got 2 moles of carbon monoxide, here we're only representing 1 mole. So what we would need to do here is to make a copy of this. And so now we have 2 moles of carbon monoxide. And then let's move on to the oxygen side of things. And so here for this second molecule here, we've got 1 mole of oxygen. Notice oxygen has 2 of them, 2 of those oxygen atoms. And so we'll need, and then we'll put the other dot for the other oxygen, so that'll give us 2. And we only need 1 copy because we're only showing 1 mole here, so 1 copy is fine. And then in the product side, we're going to need a molecule that is composed of 1 carbon and 2 oxygens. So let's go ahead and draw that first. So we'll have 1 carbon, and then we're going to have 2 oxygens attached to that. Let's do 1 there and 1 here. In that case, in fact, let's go ahead and put these slightly different. Let's put these here on this side, on the left, and on the right. And because of the coefficient here, we need 2 copies, and so we would need to put that here as 2 copies. And so there are 2 copies that represent this. Now, this is the proper representation based on what we see. So 2 moles of carbon monoxide, we've got 2 moles, 1 mole of oxygen, we've got 1 mole, 2 moles of carbon dioxide, 2 moles of carbon dioxide. Oftentimes, you're going to be asked to look at various different ways of representing the different molecules. And so what you would need to really just consider here is, can I have multiple copies of these? So clearly this is a direct representation of each of the molecules here, but what if we actually had multiple copies? So as long as the ratio is the same, we could actually have 4. We can have another ratio here of this one here like that. And then we can have another here of doubling is of the last one here. So here, this would also be a correct representation here because the overall number is 2 moles of carbon monoxide for every 1 mole of oxygen. So here we would have a ratio of 2 to 1. So in this particular case, we've got 1, 2, 3, 4. So 4 is twice the number of the carbon monoxide here. So then twice the number of the oxygen in this ratio would be 2. So this is fine so far. And as long as we can see here, the coefficient for the carbon monoxide is 2. The product is 2. So notice here we've got 1, 2, 3, 4. We would expect to have 4 at the very end. When you have a scenario where this is not represented correctly. For example, in this one here, notice the ratio here is 4 to 2, so this side of the equation is correct on the right-hand side. But when you look at the product, 2 is not correct. We would expect to have the 4 here of the carbon dioxide, which is going to be the better and the accurate representation. If this were an answer choice here for this particular problem here in this particular diagram, this would not be correct. So the way we would put that and make it correct here is we would have to actually put that as a, we would have to make sure that the bottom or the last part here has double, and then this would be correct here. All right, so this is the way you actually do this particular section. It's just making sure that the right number of atoms are represented for each individual molecule, and then as you have a complete reaction, that you actually have the right number of overall molecules being represented in that particular drawing. And so oftentimes you'll have this in multiple choice problems. And then on occasion you'll see them also in the FRQ, but typically these are often common multiple choice problems that you'll encounter. So that brings the review for 4.3 to an end. Catch us in the next section where we'll look at 4.4 and we'll continue with our discussion of physical and chemical changes.